but we will see. Okay. Coolmathgames.com. No. All right. So when we go to the motion part, so when we have multiple forces acting on an object, we are supposed to sum them up and see whatever's left over. Okay. So if I have a person that's pushing this box on the skateboard, if I pause it, and I apply a force, what direction should the box move? So the box should move to the right because as of right now, there's nothing opposing the motion of the box and the skateboard. Right? So if I push the skateboard, it's going to move in that direction. Right? So what I want to show you is when I hit play, I want you to notice that as long as the person is pushing the cart, the speed of the cart or the skateboard in the box is going to continually increase in the magnitude. Like the speed is going to increase. So we're assuming there's no air resistance. Cool. So if I've got 50 kilograms here, I'm applying 50 newtons of force, and there's nothing counteracting it. So we should be able to figure out what the acceleration is. Okay. So what when I hit play, I'm gonna switch over to another screen because it's gonna appear that it's not. It's gonna look like the skateboard is moving at a constant velocity, but it actually isn't. So I'm gonna switch screens. So when I come back to it, you'll notice that it's actually moving quicker. And take note of how the surface here looks. So when I hit play, and then I'm going to switch over to another screen. And then when I go back, it's moving. Okay, cool. Let's switch back here. And I'm not clicking anything else. I'm just letting the simulation run. And when I go back, notice he's moving quicker. Go back here. And then last time. So would you guys agree that as time goes on, he's moving quicker? And if that's the case, then did he just do the splits? That was weird. Yeah, he is moving mountains. So as time goes on, the magnitude of his speed is increasing in value. Cool. So what I want to kind of discuss is figuring out what the value is for the acceleration. All right, so the amount of force that I applied for the box, whatever. Yeah, we'll do this. All right, so we're going to do three different kinds of situations. So with the box, we have 50 kilograms. So it's going to be right here because that's the mass. We applied 50 newtons of force. So what would the value of the acceleration have to be? If I was going to solve for A, what would that value have to be? $50 times what equals 50? Yeah. So I would have an acceleration of 1 meter per second squared. So for every second that passes, I'm going to be increasing my velocity by 1 meter per second every second. Make sense? Now, in the simulation, if instead of a 50 kilogram box, I put a 200 kilogram refrigerator, and let's reset it. And then I'm going to pause it. I'm still going to apply 50 newtons of force. So what should we expect how would the motion be affected? If I'm applying the same amount of force, but I've increased the amount of mass by a factor of 4, how would it would be slower, right? So if I have a situation where I'm pushing something that's heavier with the same amount of force, it's going to move slower initially, right? Like that's logically what we would expect. So let's test it. So in fact, he is accelerating at a lower rate. Does that make sense? So let's see if we can prove that here. So we have the fridge simulation here. So we still applied 50 newtons of force, but we went from 50 kilograms and we went and increased it to 200 kilograms. So what would the value of the acceleration have to be in this situation? So 200 times what equals 50? And if your brain can't do that kind of fraction, think about it like this. If I'm solving for A, I get everything else on the other, from that side. Say again? Yeah, it would be 1/4. So not 400. So, oh no. So if you think about it like this, if I want to get A by itself, I divide both sides by 200. So 50 divided by 200, that reduces down to 1/4. So acceleration of 1 meter per second squared is a greater value than 1/4 a meter per second squared. So that means that if I increase from 50 kilograms to 200 kilograms, my acceleration is going to be a lower value, which is verified by what we just did. Cool? Yeah. Mm-hmm. Go ahead. So a lower value for the acceleration means that it's not going to increase its speed. Yeah, it's not going to increase its speed as quickly. Make sense? Yeah. All right. So instead of, let's do this. So if I remove that, I put the original box back on. But in this situation, I'm going to apply 100 newtons. So I'm doubling the amount of force, but I'm keeping the original mass of 50 kilograms. So let's figure out what the acceleration should be, like how it's going to relate to the first two situations. So if I've got 100 newtons of force, 50 kilograms, I want to figure out what the acceleration is. So I divide both sides by 50. Cancels there. So 100 divided by 50 gives me 2 meters per second squared. So this one should move the fastest out of the previous two. Make sense? So if I hit play, notice how the speed is increasing much quicker than the original one. Does that make sense? Okay. So, are there any questions about that? Everybody good? All right. I'm going to assume that you are. So, what I want to talk about now is a term called the normal force. So does anybody know what the normal force is? So it's related to the force of gravity, yeah. Um, so here's the situation. If I have a surface like that, and then I have a box resting on that surface. If I have an object is typically made of matter, right? And if I have matter present, then I therefore have mass. Would everybody agree with that? If I have mass and I'm on Earth, then gravity is going to be acting on that mass. So what we do is we represent that force due to gravity pointing down. Okay. So this is the force due to gravity. And in everyday speech, we refer to this as weight. Okay. Any questions so far? So, according to this picture as of right now, is this balanced or unbalanced? So, Uriel says it's balanced. So, if I have one force, how can it be balanced? Does that make sense? I think you might be thinking a little ahead. So, just according to this picture, is this picture balanced or unbalanced? It would be unbalanced because there's only one force. But we know that if there is a box sitting on the floor, we can observe that the state of motion of that box is not changing, right? It's currently at rest and it's not moving. So we can therefore conclude that all the forces acting on that box cancel each other out, i.e., my net force is zero. Everybody agree with that? If my net force is zero, the state of motion of the object will not change. So we're missing a force to cancel out the force due to gravity or the weight. So according to this diagram right now, this box would move to the center of the Earth. What is your gross force? Funny. So what's preventing the box from going to the center of the Earth? Yeah, the surface, right? The surface that it's resting on. It's preventing it from moving into the Earth. So what I'm going to do is I'm going to say this is, whoops. That was weird. Sorry about that. Peter spazzed out for a second. So this is going to be force due to the surface. So it's not surface tension. I don't know if you're just being smart. But if you think about it as like a book resting on a table, gravity is going to be acting on the book, trying to pull it through the table, but the table is preventing it from going into the earth, right? So the table is pushing back onto the book. So same kind of deal with this. The surface is pushing back on the box. Everybody cool with that? So anytime that there is a force being reacting to, or a force that's being imposed on an object from a surface, we're going to refer to that as the normal force. Okay. So the word normal isn't referring to like ordinary or just run of the mill kind of deal. The word normal is referring to the mathematical definition of normal. So if I have a line like this and I wanted to draw a line that is normal to that line, it would be something that is perpendicular, or in other words, 90 degrees to the surface or to this line. Does that make sense? So the force that the surface is imposing onto the box is 90 degrees to the surface. That's what it means for the normal force. Any confusion about that? But it's hot. I don't understand. So this is for a horizontal surface. Now, what would happen if we had a vertical surface? Now, this one gets a little interesting. So, if I have a surface like so, and then I've got my box, what was that? A weird noise. Okay. So if I have an object, the box, and I'm applying a force to this box, well, think about it like this. In this situation, I've got a box and I'm pushing it up against the wall. And this picture that I've just drawn is taken the instant that I take my hand off of the box. Okay, so like the nanosecond immediately after I remove the force of my hand pushing the box against the wall. Is everybody okay with that? Everybody understand the situation? So, in that particular situation, what are the forces acting on this box? If I have a mass and it's on Earth, the force of gravity is always going to be affecting it. So the force of gravity is going to be present. And this is the instant that I have removed my hand. So there's no force pushing it into the wall anymore. So that's not there. And since I'm not pushing into the wall's not pushing back. So what is it like? We're also assuming that there's no air resistance. So are there any other forces acting on the box in this situation? So that's what this is. So gravity is pulling it down. So as of right now, the only force that's acting on it is just gravity. Cool. So if that's the case, what should we expect the box to do? Is this balanced or unbalanced? Is it? With an un. Yeah, so this is unbalanced. The only force that's acting on it is the force of gravity. So in this situation, we should expect the box to fall, right? According to this diagram, the motion of this box should move down because there's only one force acting on it, and it'll move in the direction of that force. And in real life, the instant I take my hand away from the box falls. Are we tracking so far? Okay. Now, this is where it gets a little interesting. So if I push the box, so if I push in the box like so, I know that the box isn't somehow morphing through the wall, right? We're assuming that we're not in the matrix and that this is just normal, ordinary life. And when I push a box against the wall, it's not going to trans like go through the wall, right? It's going to stay where it is. So if I'm applying a force into the wall, and I know that the harder I push, it's still not going to go into the wall, there has to be an equal but opposite force pushing back to cancel out my pushing force. Does that make sense? So what would be causing that blue force? This would be the normal force, the force of the surface pushing back on the object. Cool. So if I'm holding a box against the wall, it's not moving horizontally. So I therefore know that the sum of the forces in the horizontal axis must balance out or equal zero. So the magnitude of my push should equal the magnitude of my normal force, but in opposite directions. So for instance, this could be 50 newtons or negative 50 newtons because it's going to the left. This would be positive 50. I just pull those numbers out of thin air. Does that make sense? So when I add those two together, it will equal zero. My net force will equal zero. Now, if I'm pushing a box against the wall, if you think about it like as a thought experiment, if I'm pushing it against the wall, it's possible that I can do that. Just hold it still, and it not move. Do you guys agree with that? Like I can push a box against the wall and it stays there, pushing up against the wall. It's a pretty believable situation. So, according to this diagram, would this diagram represent that physical situation? In other words, are all of the forces accounted for in that thought experiment situation in this diagram? So in the horizontal axis, the push and the normal force are present. Cool. So because I know it's not moving in the horizontal axis. But if you think about it, if I'm pushing it against the wall, is it moving vertically? Is there any movement of the box in the vertical axis? No. So if I'm pushing something against the wall, or, yeah. So if I have my phone case, I push it against my hand, is it moving up or down? If I push it like this? No. So the force push, and then my hand is pushing back to counteract my pushing force. Gravity is present because I've removed my pushing force and it fell. So I need something that is counteracting this gravity, right? So if I look at the diagram, I need something that's canceling that force due to gravity. So in other words, I need to have a force like that. So what is creating that force? Anyone? Go ahead. So gravity is the red one. Gravity is pulling it down. So gravity is always pulling, it's never pushing. What was that? So here's a box. This is a wall. What do you mean by the other thing? Yes, friction. Good. So if you think about it, would it be easier for me to hold a we'll say a cardboard box, right? Some thick cardboard, and it's in a nice cube, and it's not going to like crush when I push on it. Would it be easier for me to put 5 pounds into that box and then push it against a wall that's lined with sandpaper, or a wall that is greased up with we'll say petroleum jelly, right? Would it be easier for me just to push completely horizontally on the sandpaper or on the one that has lubricant on it? Which one would require less effort from me? Correct. The sandpaper, right? So the sandpaper is going to be more rough, more grippy or frictiony if you're pushing it straight in a straight force. It wouldn't matter. It actually would. Because if I, or think about it with ice, right? If I have like a plastic box, right? A plastic cube, and I push it against a wall with sandpaper, if you're wobbly, yeah. So think about it. All right, how about this? If I have a situation where I've got um, a wall with different materials, right? So I've got sandpaper, I've got sheet metal, and then I've got ice, right? Just a wall of ice. And I've got the box, and I've got a little force sensor pushing on the box, and then I start decreasing the amount of force being applied to the box. Which one would fall first? So if I've got a wall, so I've got sandpaper, I've got metal, and then I've got ice. All right, so sandpaper, ice, right? And then I take a box. And I take the box and I'm pushing against the sandpaper with a little machine, right? And it's a constant pressure, and then I start decreasing the amount of pressure being applied to the box against the wall. Which one of these situations, the sandpaper, the metal, the ice, would the box fall first? Yeah, it would be the ice, right? So the ice is going to be the slickest, right? You disagree? All right, so let's forget about the metal. Sandpaper and ice. How about that? You want? Okay. So it actually wouldn't. Ice is more slick. Um, mm. Let's do metal and sandpaper. How about that? Is that better? Okay. So metal and sandpaper. So if I did the experiment and I was pushing into the metal, it would drop, like if it was doing them at the same time and it was pulling back the amount of force, the one with the metal would drop quicker because there's less friction, right? Um, so what this is going to lead up to is, whoops, and I want to kind of show you what how I did that. So I've got a capital F, then I've got a script F to represent the force due to friction. And how I did the script F, it looks like a little weird S, and I do a horizontal line. Cool. So this is the force due to friction. Cool. So if I push push the box into the wall, it's going to smush the box and the wall together more and more and more. Cool. So there's going to be a relationship between how much I push to how much friction is present. Does that make sense? So if I lightly rub my hand against some sandpaper, it's not going to hurt as much. But if I push into it and I drag it down, it's going to really hurt, right? Because there's more friction. I'm applying more force. I'm squishing those two surfaces close, like more and more together. It's causing more friction. Any confusion about that? Okay. So, really quick, I want to explain. So the difference between the metal surface and the sandpaper was the type of material it was. Would y'all agree with that? It's two different materials, and they both have different levels of frictioniness. Make sense? One is more frictiony, one is less frictiony. I know that's not a real word, but whatever. Um, so how we kind of, what's the word, assign a value to the amount of friction, how frictiony a surface is going to be the coefficient of friction. Cool. So this coefficient of friction has to be greater than 0, but also less than 1. All right. And the symbol that we use to represent the coefficient of friction is the Greek symbol mu. Does that make sense? So mu represents how frictiony a surface is. The greater the value, the more frictiony it is. So if I've got a rubber mat, it's going to be closer to the value of 1, but still less than 1. It's going to be like 0.7 something. And then ice would be closer to 0. Or something that's very, very polished metal. It's very little friction. That's going to be a lower value. Are we cool with that? Okay. So the last thing that I want to talk about is the two different types of friction. There's going to be So the force due to friction, like force due to friction with the subscript of S, and then with the subscript of K. So does anybody want to take a stab at what those represent? Mm-hmm. So remember, subscripts represent like a different attribute. Um, so they're both force due to frictions, but this is according to something and something else. Cool. Now, here's an example that demonstrates how both of these can happen in the same event. Okay. So there can be this type of like, there could be this friction and this friction, not at the same time, but in the same event, same situation. So, how many people have tried to move a large piece of furniture across carpet? Like trying to move a TV stand or a couch or a bed or something heavy, a big heavy box. Try to move yourself. Oh, you're saying that you've done that before. Okay. Um, so when you start to push the object, is it when is it easier to push? When it's starting from rest, or once it's already started to move? Right. So once it breaks free and it starts to change its position, it's a little bit easier to push on it, right? Has everybody experienced something like that? Yeah. So it's more difficult to get it to start to move, but once it starts to move, it's a little bit easier. So that's what this is dealing with. So the S represents static or stationary. That's what static means, not electricity. So the force due to static friction or stationary friction or friction at rest. And then this one would be kinetic. Or friction, you spelled kinetic wrong. Um, Friction due to movement. Cool. So what I plan on doing is I have a demonstration. There it is. So I've got a demonstration that I did during, like when we were in the classroom. But obviously we're not in the classroom right now. But I've kind of this experiment has kind of evolved. So I want to kind of explain what it is. So this lab was the friction lab, and it was supposed to demonstrate the difference between static and kinetic friction. So what I did was last year I made these little carts, like little sleds, and what we did was we put masses inside the cart or the sled, and on the bottom I put some of the it's like a foam. Uh, I don't know what you call it, but you put it in like tool chests to keep things from sliding around. So it's designed to create more friction. So I have that on the bottom. And then what we did was we put masses in here. Like I already got the force to gravity of this because this is going to be pushing down already. And then we added masses onto here. And then I took my yo-yo string because this string is very good about not stretching. Um, so I put on the eye hook, and then we had these on the science tables, which are very smooth. And I attached this to the edge of the table, and then on the other side, down here, we had a force sensor. So when I pulled on it, it would show, it would plot how much force is being applied as time progresses. And there would be a couple of students that would be doing this lab. There would be one student designated to have the device and pull down very carefully. And then once the object broke free and started to move, then there was somebody that was observing this, and they would notify the person pulling it that it started to move, and then they would have to move it at a constant velocity, and then it would produce a graph. And then we would take that data, the data that was plotted, and figure out what the maximum amount of force was required to make it move. And then we could figure out the coefficient of static friction from that. And you could also do kinetic, but I didn't do that. So what I plan on doing, I've got the devices charging right now. I'm going to try to set it up so I can do that demonstration where I can have the webcam set up so you guys can view this and then also see the data being plotted in real time. Like as I'm pulling it, like there might be a camera on this and then a camera on me pulling it down, and then also the graph. But I need to work that out. I don't know how I'm going to do that yet. So yeah. But then like what we'll do is I'll try to do that demonstration, and then I'll give you guys more information about the force due to friction and how it's related to everything else. Cool. All right. Let me go ahead and end the stream real quick.